Hey everybody, welcome to today's lesson. Today we're going to be talking a little bit about parts per million. This is another form of concentration, and I thought we could start with a real world application. So taking a look at the screen or at the guided notes sheet, however you're following along, notice that I've included here a TDS material maximum acceptable level. TDS stands for total dissolved salts, and they are made from compounds that will dissociate or break apart or ionize, okay, in the water in order to form mobile ions. Um, TDS are the ions that cannot be removed by a traditional filter. This means that our drinking water that we get from our tap even has some total dissolved salts in it. Uh, because of this, right, those levels need to be monitored in order to make sure that whatever we are consuming is at a healthy and acceptable level. So the EPA, or the Environmental Protection Agency, monitors the safe level of total dissolved salts that can be found in our drinking water. Now, in New York City, what I think is particularly cool is you can find these water testing stations along the streets. They kind of look like a little box, like I don't want to say a mailbox because it's not the shape of a mailbox, but they're like little boxes that are kind of on posts in the street. And if you read closely, it'll say water testing station. So I think it's cool that you can see those on the streets. Every year, though, or every couple of years, our school has to undergo testing in order to see if all of the different faucets, what the level of the TDS coming from those faucets are, particularly the lead levels. And if you're following, or if you follow the news, right, these ideas of lead dissolved in the water actually um, uh, happens often where water is deemed not acceptable. And the case that comes to mind is really Flint, Michigan, and the issues that they've had with their water. So if you're not familiar with it, look into it. It's very unfortunate. So let's take a look. So our school underwent testing for total dissolved salts. Every single faucet gets tested, every drinking fountain gets tested, and the one in my room had contained 8.0 times 10 to the negative fifth grams of lead. And so I was curious, is this water deemed safe? How do we know? So the first thing that I want to consider is, why would we not use molarity in order to account for this concentration? Why would I not use molarity in order to calculate total dissolved salts? Why are we in a different unit called parts per million? And if you think back to the molarity video that you watched yesterday, okay, remember, molarity is used for larger quantities of solute. If we have something as small as 8.0 times 10 to the negative fifth grams of lead, that's a very teeny tiny amount of solute. And what would happen is the amount of the solvent, okay, or I'm sorry, the amount of the solution would have such a small amount in that the molarity would be very, very small. So molarity is not used because, okay, the concentration of the solute is so small, okay? And so we use parts per million. Now, before we get into parts per million, though, I want to take a look at percent. So how do I calculate a percentage? Well, percent is going to be the mass of the parts, or mass of whole, or I guess that's, percent by mass, which is what we use in this class, but you could do part over whole, right? So just part over whole. Like if I asked you to calculate the percentage of people that chose blended versus remote learning for this year, you could do the number of the people, right, that chose blended over the total number of students to figure out the percentage of blended, or number of students that chose remote over the total number of students in order to calculate percentage of remote. So it's just part over whole. But the key here is that we have to multiply it by 100, okay? And so if we were to think about breaking down the word percent, right, the prefix per and the suffix cent, how does this calculation make sense to us? Well, per typically indicates of, and cent means 100, right? So per means of, and suffix or cent means 100. So this literally means of 100. Hence why we multiply it by 100. Okay, because we're looking at if the sample were of 100. Now, how do we think we're going to calculate parts per million then? Well, if you think back to percent, let's use that to derive our equation. Now we're talking about per million. So parts per million, abbreviated ppm, is calculated, okay, mass of part, okay, over mass of whole, multiplied by, you guessed it, 1 million. Okay, so parts per million is literally like a percentage calculation. Just instead of multiplying by 100, we multiply by 1 million. So let's go ahead and take a look at a practice problem or two before I call this lesson over, or before we look back to see if the drinking water is safe. So calculate the total mass of solutes, okay, in a 100-gram solution that is 15 parts per million. So looking at our equation, okay, ppm equals mass parts over mass whole and multiplied by 1 million. Okay, so what we're going to do here, let's plug in all of our values. So we have 15 parts per million is equal to X, we don't know the mass of the solute, over 100 grams of solution multiplied by 1 million. Okay, so what we're going to do first is we're going to go ahead and divide by 1 million on both sides, right? This way we know that we are isolating our variable. Okay, so we have 15 divided by 1 million, which is going to give us 0.0000015, okay, equals X over 100. So we're going to multiply both sides by 100, okay, and that's going to give us a total of X equals 0.0015 grams of lead. Okay, awesome. Let's go ahead and take a look at another example. So 0.00432 grams of nitrogen are dissolved in 100 milliliters of water. Express the concentration in terms of parts per million. Now, here's a trick to this question. So again, we can think of our equation, mass of part over mass of whole. Let's go ahead and set this up. We are solving for parts per million. Okay, our mass of our part, we're measuring the grams of nitrogen, or we're interested in the parts per million of nitrogen. So we have 0.00432 grams of nitrogen are dissolved in 100 milliliters of water. Now, this is a problem here, okay? Milliliters is not a mass measurement. However, the density of water is about 1 gram per milliliter, which is nice because that means that each milliliter should weigh about 1 gram. So that means that 100 milliliters is equal to 100 grams. Now, we are still not done with our total mass here, and this is definitely the trickiest part about parts per million. Okay, looking at our problem, we have 0.00432 grams dissolved into 100 milliliters of water. So our water itself weighs 100 grams, but the nitrogen adds to that total mass of 0.00432 grams, okay? So you do have to account for the fact that it is not going to, that you do have to add that in and that it's already not accounted for. Now, you might be thinking, well, why then in problem 1 did we not have to consider that? If you look at problem 1 here, it says that what is the mass of the solute that was contained in a 100-gram solution? So the whole solution itself weighed 100 grams. The difference is this keyword that it is dissolved in, okay? It is dissolved in. So the solution already contained the mass of the solute in problem 1, but in problem 2, it did not. So we then have to go ahead and solve for this, but we multiply by 1 million at the end, right? Parts per million. So let's go ahead and figure this out. So 0.00432, okay, divided by 100 plus 0.00432, okay, multiplied by 1 million is going to give us 43.2 parts per million. Okay, excellent. All right, so this leads us to our last problem, which is the water in the classroom safe to consume according to EPA standards? Now, going back to the top of our notes, we have our mass of our lead, but it should, or I should have included on the sheet, and I didn't, what the total sample taken was, because that does become very important, right? We need to know the mass of our total sample. So this was in a 100 milliliter sample, okay, taken, which means that already included the lead dissolved into it. Okay, so let's go ahead and fall back down to the bottom here and calculate and see if this is in fact safe. So we have parts per million equals, okay, 8.0 times 10 to the negative 5th grams divided by, again, 100 milliliters is about 100 grams, okay? If you're not comfortable with looking at this in scientific notation, that's going to be 0.00008, okay, grams divided by 100 grams multiplied by 1 million, okay? And this is going to give us 0.00008 divided by 100 multiplied by 1 million, giving us 0.8 parts per million. And so to determine if it's safe, let's go back and check our chart here. So according to the EPA, our dissolved lead levels can only be 0.05 in order for it to be maximum. 0.8 is greater than 0.05. So no, this is not safe to consume. Now, I do want to tell you that this has since been fixed. This is not an issue anymore. What happens is if a sink goes unused for a long amount of time, sometimes the levels measured can be much higher because of the pipes, the water sitting in the pipes. So the water was let run is the best way to say this, and has been since cleared and it is deemed safe, though we don't really consume the water from the sink in the classroom anywho. So anyways, guys, thank you so much. Have a great rest of your day, and I will see you guys tomorrow.